join. Wait 5 minutes for others to join. So wait also for the others to join. So we start our class. Bismillah ar-Rahman ar-Rahim. Wassalatu wassalamu ala ashrafil mursalin. So please don't forget to make the attendance online in future. Please make the attendance online. Okay. So we will continue our topic of fundamental of algorithm. So here important problem times. Here we have sorting, rearrange items of a given list in a certain ordering, example ascending or descending. Searching, dealing with finding a given value called a search key in a given set or multi-set. String processing typically involves of comparing string or called string matching. And graph problems, any problem that can be represented via a collection of points called vertices and their connectivities called edges. Combinatorial problems, a more complex problem that asks to find a combinatorial object such as a permutation, combination, and subset. Geometric problems dealing with the geometric objects such as points, lines, and polygons. Numeral problems dealing with mathematical objects of continuous nature, solving equations and system equations, computing defined integrals, evaluating functions, etc. So here we have this kind of problem types that we're going to study in this course: sorting, searching, string processor, graph processing, combinatorial problems, geometric problems, numerical problems. So here, describe characteristics of an algorithm. So algorithm is efficiency. We study the efficiency of the algorithm, time efficiency, and state efficiency, and simplicity and generality. Okay. Also have correctness. So a step of algorithm problem solving. We have understand the problem, then decide on computational side on computational means exact versus accurate solving data structure, algorithm design technique. Then we go to design algorithm. Then we go prove algorithm correctness. Okay. Then here analyze the algorithm. Then we go back to here again to make the algorithm design technique. Then here, last thing, you have code algorithm. Code algorithm. So first of thing, you have to think the logic. Okay, then I write the algorithm, the code. So what is an algorithm design technique? Algorithm design technique or strategy or paradigm is general approach to solving problems from different areas of computing. Okay, so what is the algorithm design technique? Algorithm design technique or strategy or paradigm is a general approach to solving problems algorithmically that is applicable to a variety of problems from different areas of computing. Method of specifying algorithm. We have pseudocode and we have is a mixture of natural language like constructs, flowchart. So you have pseudocode and flowchart. A method of expressing an algorithm by a collection of connected geometric shapes containing descriptions of algorithm steps. So you have flowchart and you have pseudocode. Okay. Why we need algorithm to measure how good the algorithm, complexity of the algorithm, correctness, and time efficiency and space efficiency. To benchmark the algorithm complexity for future improvement, lower bounds, and optimality. Okay? As a mechanism to compare and choose the appropriate algorithm for further implementation. Analysis of algorithms, issues, correctness, time efficiency, space efficiency, and optimality. Approaches, we have a theoretical analysis and empirical analysis. Okay. Before I move to the gear complexity, I want you to solve this question. Okay. Draw a flow chart. Draw a flow chart. Okay. The question is uh, in the chat box. Draw a flow chart for finding the total numbers of males, females from the visitor from the visitors and print the result. Here we have print type X to print. Okay, draw a flow chart for finding the total number of males, females from the visitors and print the result type to print. Here, the result type X to print. Okay, so you have to X, letter X to print. Okay, please, I will give you 10 minutes to, or 5 minutes to solve this before I continue. Okay, so you have 5 minutes to continue solving this question in the chat box. Okay, the question is also on the screen. So who finished drawing the flowchart? It is an easy question. Who finished writing drawing the flowchart? So who finished answering? Please share your screen. If someone finished answering your question, please share your screen. No one? Please try to solve the question and share screen if you are available. If you want to share your screen, please. Any volunteer share his screen? So here, what we have to do, we have to have a loop, and we have to exit the loop using x. Am I right? So here I can solve this one. This one start. Then we have input, input, gender, input gender. Now we have so here this one. Then here what you have to see, insert text. If gender here gender equal to M. If gender equal to M, what I have to do?
M plus 1.
Okay. So here M equal M plus 1. Here M equal M plus, okay. Here, if the answer is yes, if the answer is yes, so if it is yes, if it is yes, m equal m plus 1. If it is no, if gender equal, if it is no,
F equal F plus 1.
we check. If it is no, we go here to if it is no, we go to another question. Gender equal F means female. What I have to do?
F equal F plus 1.
So here, what is the answer? As you said here, F equal F plus 1. Okay? If no, what you have to do? Hmm?
Go back to input gender.
If no, if gender M, if gender equal to if no, I have another question. If no, if gender equal X, what I have to do? If yes,
Print.
print. Here, if yes, First of all, I'll say total equal m plus f. Then print what? F and print print total m f. Then we have here if gender equal no. What we have to do if it is no? So here if it is input
Loop.
gender m plus 1, f plus 1, x total m plus f, because here type x to print. So here if no,
Loop.
we have to print invalid input. Print if not x, not f, not m, so print invalid input. Okay? Then what I have to do, I have to go to gender again. Okay? I have to input the gender again. Insert. But before I make start, I will put here values for M and F and I mean initial values. What is the initial values? After start, M initial values M equal F equal total, or M equal 0, F equal 0, and total equal 0. Am I right?
Yes.
Yes.
So this is a simple flowchart. Okay. So now start M0, total 0, input gender, gender male, M plus 1, F here. Here print here. Then after this, I go, if no input, invalid input, then I will go here to insert the value of input again. Input gender again. Here also after putting M, I will go to here. Same here. After input, we go okay. Now here, if yes, M plus 1, if gender F, F plus 1, if gender X, yes, total M plus F, print total M and F. As if it's not M or F or X, print invalid. Okay, then go and put gender again. Then here, what we have to do, what is the last thing? Here I will make like int. Int. Okay, so here the start. Okay, so here, do you agree with this algorithm flowchart? Do you agree with this flowchart?
Yes, Captain.
Okay, so here I think we cover all the options, and then we have here we have the gender and how to think to solve this simple question. Okay? Now, we continue our so here complexity refers to the rate at which storage or time grows as a function of the problem size, typically n. So the rate in which storage or time grows as a function of the problem size, typically n. Two important measure, one time complexity and space complexity, can be measured by two mechanisms. Machine dependent, the absolute growth depends on the machine compiler used to execute the algorithm and other factors. And machine independent, the growth expressed by the complexity in terms of its relationship to some non-functions based on a proportionality approach and formally known as asymptotic analysis. Based asymptotic analysis, what is asymptotic analysis? Asymptotic analysis is based on the idea that as the problem size grows, the complexity will eventually settle down to a simple proportionality to some non-functions incorporated in the big O, big omega, big theta. Big O relates to an upper bound on complexity. Big omega relates to the lower bound on complexity, and big theta relates to a tight bound on complexity. So you have big omega, big O, and big theta. What is asymptotic analysis? In mathematical analysis, asymptotic analysis is a method of describing limiting behavior. In computer science, in the analysis of algorithm, it is to estimate the performance of algorithm when applied to very big input data sets. If a study to the behavior of the input when they are very large, considering a function fn, is when there is a need to describe its properties as n becomes very large. Okay, so it is a study to the behavior of the input when they are very large, considering the function n, is when there is a need to describe its properties as n becomes very large. If n equal to n power 2, the function fn is said to be asymptotically equivalent to n power 2 as n go to infinity. In estimating the running time of an algorithm, we may end up the asymptotic behavior as the growth of fn as n gets large. Example, function fn, say multiply n power 2 multiply k for some constant factor of c and k. It is said the algorithm to be asymptotically equivalent to n power 2. So if I have this constant and here n power 2, I will take n power 2 as n go to infinity. Okay? It is not important to know the constant factors because they would not affect the upper bound. So here it is not important to know constant factors because they would not affect the upper bound or lower and tight bound of running time. Example, fn 3 multiply n power 2 plus 100. So what is the big O? Big O is n power 2. So the constant will not affect the value of the n when n goes to infinity. Okay, most important order of growth within a most important order of growth within constant multiple as n goes to infinite. Example, how much faster the algorithm run on computer that is twice as fast? How much longer does it take to solve problem of double input size? So here we have a fast computer. Here we have double the size of the problem. if if you have 1000 item, so here if I run this one, so in different machine, or maybe if I have 1000 and I have 2000, or how will get the behavior of the algorithm. So here basic asymptotic efficiency classes. One, we call it constant, log n logarithmic, n linear, n log n log n power 2 quadratic, in power 2, and power 3 cubic, 2 power n exponential, n factorial. So basic asymptotic efficiency classes, TNOA O1. This is called constant growth. Tn does not grow at all as a function of n. It is a constant. For example, array access has this characteristic. The operation AI takes the same number of steps no matter how big A is. Tn O log n, this is called logarithmic growth. Tn grows as the base 2 logarithm of n. Actually, the base doesn't matter. It's just traditional to use base 2 in computer science. For example, binary search has this characteristic. So here O log n is the characteristics of binary search. O constant is O1 means constant. O log n, and we have Tn, On. Here you have O1 log n and n. This is called a linear growth. Tn grows linearly with n. For example, looping of over all the elements in a one-dimensional array would be an On operation. Okay, Tn On log n. This is called n log n growth. Tn grows as n times the base 2 logarithm of n. For example, heap sort and merge sort. Heap sort and merge sort have this characteristic. So, what is the complexity of merge sort? Is n log n. N log n. What is the complexity big O of bubble sort? Bubble sort is n power 2. Tn On power k. This is called polynomial growth. Tn grows as the k power of n. Selection sort is an example of polynomial growth rate algorithm. On power 2. Tn T power n, is this all exponential growth? Tn grows exponentially. It is pronounced out big O of t to the n. Exponential growth is the most feared growth pattern in computer science. Algorithms that grow this way are basically useless for anything but very small problems. Okay, it can solve any just small problems, because when we increase the number of the problem n, it will increase exponentially. That is, it is very fair to in computer science. Algorithms that grow in this way are basically useless for anything but very small problems. In computer science, we traditionally use the constant 2, but any other positive constant could be used to express the same idea. Tn On factorial, this is called factorial growth. Tn grows factorial. It is also the most varied growth pattern in computer science. So here, if n equal n 10, n equal 10 power 2, power 3. So what is here the values? Here, look, binary log to n is 3.3, n equal 10, n log related to or n 3 times 3.3 times 10. Here 10 power 2, 10 power 3. Here 10 power 3 to power n, and 3.6 multiply 10 power 6. Okay, if 10 power 2, we have 6.6. 10 power 2, 6.6 multiply 10 power 2, 10 power 4, 10 power 6, and 1.3 power 30. factorial n dot 3 n point 3 multiply 10 power 157. So here this is the constant. This is O log n. Here On linear. Okay, O log n. We go like this. This is O log n. This is constant. This is linear. This is O n log n. Here O log n. Here O n log n. Here A n power 2. Here O n power 3. Here O n factorial. And we have also 2 power n. We didn't measure here 2 power n. Probably exponentials. So here we have Tn 60 n power 2 plus 5n plus 1. So if 10 here, asymptotic analysis 10, here will be 6,000. 6,000 plus 50 plus 1. So 6,051. Here 60 n power 2 will be 6,000. N power 2 will be 100. 100, this is will be the value. 1,000, this is will be the value. And 1,000, 10,000 will be this value. Okay? So if we have something like this we call it asymptotic analysis. Here we have n power 2. Here we have 60 n power 2. And you have this formula 60 n power 2 plus 5n plus 1. This line. Okay? This is asymptotic analysis. So here we have Fn, OGN. Here we have CGN, Fn, and N. Let me see what is the big O. What is the big O for Gn? We have Fn, we have OGN. So here OGN, Fn, there exist positive constants C and N0 such that 0 is less than Fn is less than CGN. So here we have Fn. There is this positive constant C and N0 such that 0 is less than equal Fn is less than GCN. This one CGN. This one for N greater than N0. The big O notation defines an upper bound of an algorithm. It bounds a function only from above. Okay, so this one, example, ancestor sort, worst case is On power 2. Best case On. Okay, this one, CGN, this is this OGN. We have CGN constant, that is Fn is less than here 0 is less than greater Fn. Fn is less than greater Cgn, and Fn is less than equal Cgn and greater than equal 0. This one we call it big O. Big omega Gn, Fn there exists positive constant C and N0 such that 0 is Cgn and Cgn is between Fn and 0. Here in the previous graph, Fn it is bounded by Cgn. Here no, Cgn, Fn and Cgn is bounded here. So here will be this one bound the big omega. Okay, here the value is here. This gray color here, the value is going up. This one CGN we have a lower bound. The big omega notation defines the lower bound of an algorithm. It bounds a function only from below. Example in statistical, because best case omega n, the omega n is the least used notation. Big theta AGN if n there exists positive constant C1, C2 and N0 such that 0 C1GN and Fn less than CGN for all n greater than 0. So we have C2GN and C1GN and we have Fn. This one we call it big theta. So I have a lower bound and upper bound, and the Fn is between. Here for big omega we have upper bound. For theta big omega we have lower bound. For theta we have upper and lower bound. The define the notation defines bound as a function from above and below, so it defines exact asymptotic behavior. Asymptotic growth asymptotic order of growth, a way of comparing functions that ignores constant factors and small input sizes. OGN, class of functions Fn that grow no faster than Gn. Theta Gn, class of functions Fn that grows at the same rate as Gn. And we have here omega, classes function Fn that grows at least as fast as Gn. So here no faster than Gn. Here OGN means no faster than Gn because we have upper bound. Theta Gn here same rate as Gn. Omega n at least as fast as Gn, because here we have lower bound and here we have upper bound. Establishing order of growth using definition. Definition Fn is in OGN, big O, if order of growth of Fn less than order of growth of Gn within constant multiple. That means there exists positive constant C and non-negative integer N0 such that F0 is less than CGN for every n greater than equal N0. Example, 10n is On power 2, 5n plus 20 is On. This is but just an example. We have On power 2 and here we have On. That's we study in our class, and we have best case, average case, and worst case. We did an example for bubble sort, and we said how many swap operations that I need. So in ascend, if the queue is in descending order, this is the worst case to make it ascending. So I will make the full comparisons. So if I have 5 numbers and 5 elements, I need 5 elements, and I need to order this in ascending order. So here will be using 10 swaps because it is in the descending order, and I make it ascending. So it will be worst case. Average case is between. Best case if the queue is already arranged in ascending order, so we need to make swap. So this is the best case. For some algorithms, efficiency depends on the form of input. Worst case, C worst n, maximum over inputs of size n. Best case, C best n, minimum over the input of size n. So here maximum over inputs, and here we have minimum over size, and here average case. So here the maximum swap is 10. Minimum is 0. Average case is here average over inputs of size n, number of times the basic operation will be executed on typical input. Not the average of worst and best case. Not the average of worst and best case. So the average not means the average between worst and best case divided by 2. Expected number of basic operation considered as the random variable under some assumptions about the probability distribution of all possible inputs. Example, sequential search. Algorithm here, sequential search, A0 n minus 1 k. Search for a given value in a given array by sequential search. Input an array A0 to n minus 1 and search a key. Output the index of the first element of that matches the index of first element of A that matches K. Okay, this is the index. We need the index. If the index here 0, 1, 2, 3, 4, so we find if match K means the position of the value. If it is no matching elements, it will give me minus 1. So here I equals 0 while I less than n and ai not equal k. Do I equal I plus 1. If I less than n, return I. Else return minus 1. Worst case, best case, average case, we need here to find this value. Best case if the element is the first element. Worst case is if the element is the last element. Average case is when the key is in the middle of the queue. Okay? I will give you example. Okay. If A equal we have 5 values 1, 2, 3, 4, 5. If the key sequential search, if the key I'm searching for 3. So what is the index? 0. So this is the best case. This is the best case. Why? Because it is the first element. When I try to search for 3, it is the first element. Okay, if it is If the key is 3, index is index is 5. This is the worst case because the key is at the end of the array. So I have to compare first one, second one, third one, fourth one, and the last one. I find it in the first one. So the worst case is 5 or not in the list. Even if it is not in the list, it will be the worst case. Means here, I compare here 1, 2, 3, 4, 5. I didn't find it. If I search for something like here 7, 7 is not here in the here will be the worst case. If each comparison cost me 10 ringgit, here I will make one comparison. I will find it is here. I make one comparison. So one comparison means 10 ringgit. So here one comparison. So I spend only 10 ringgit. Here I spend here 5 comparisons. So I spent 50 ringgit. I didn't find uh, the key. Here if the here in the middle we call it the index 0, index 4, index this one, the average. So it is not the this is not 4 plus 0 divided by 2. It is not the best of the average. Okay, it is sometimes like this. Okay. I will give you 10 minutes to write a code to find this key. I think 5 minutes is or 8 minutes is enough to write a code to search for sequential search. Sequential search. Please start coding. Try to write a code, please. You have 8 minutes to finish this code. Please don't forget to make the attendance online. Please don't forget to make the attendance online in future. You have 7 minutes to finish this one. I will come back within 5 minutes. So let's continue our class. So please, I want someone to share his answer. Who solved this algorithm? Sequential search. Who solved it? Who wants to share his answer? I think it's easy code for sequential search. Any volunteer? Any volunteer want to share his screen? Okay. Empirical analysis. That one was asymptotic analysis. This one, empirical analysis of time efficiency. Select a specific typical sample of inputs. Use physical unit of time, milliseconds, or count actual number of basic operation executions. Analyze the empirical data. Here, machine-dependent empirical analysis. Okay, this one initial and final screens of a typical visualization of a sorting algorithm using the bar representation. Okay, this one machine dependent. So this one empirical analysis. So how to do? Select specific sample of inputs, use physical units of time, or count actual number of basic operation execution, analyze the empirical data. Okay. You move to iterative analysis of iterative algorithm because before I move, I want to see if iterative means losing loops. So you have theoretical analysis and empirical analysis. Okay, let us see some exercises here. Before I move to this chapter. Okay, I have to log out and log in again. Don't know what is the problem here. Let me try to search this one. Okay. Let me go here through these slides, another slides. So we have symptomatic analysis, simplicity. Here we have simplicity, generality, finding better algorithm. Here we have empirical analysis, define algorithm efficiency by measuring using time units. Here, theoretical analysis define algorithm efficiency in terms of number of basic operations executed with related to its basic operation, theoretical and empirical. Here, basis theoretical comparing to empirical analysis. Here, mathematical reasoning and logical deductions, actual implementation, experimental results. Performance evaluation for theoretical analysis focuses on worst, average case, and best case. Empirical analysis measures time, space, or other resources based on real execution. Input works with general input size in or consider worst case, average case inputs. Here, empirical analysis depends on a specific real input and data set. Hardware dependent? No. Theoretical is hardware dependent. It abstracts away details of hardware. So it is dependent on the hardware. Here, yes, empirical analysis is dependent on the hardware. Performance is impacted by specifications. Accuracy in real world, here theoretical can give pessimistic or idealized view, abstracts away practical overhead. Here, accuracy in the real world. Here, empirical reflects real world performance but may not be generalizable to all input sizes. Usefulness, useful for comparing algorithms theoretically and predicting behavior on large inputs. Here, useful for understanding practical performance, especially for small or moderate inputs. Okay, so here useful for algorithm for large inputs. Here for empirical for small or moderate inputs. Here understand the word efficiency in practical settings. Okay. Here go understand efficiency in general or abstract scenes. sense. Understand efficiency in a general or abstract sense. This one called asymptotically, and this one we call empirical. When to use each type of analysis. Use statistical analysis when you want to a high-level abstract understanding the algorithm efficiency. Okay? A high-level abstract understanding of the algorithm efficiency. To compare algorithms across different input sizes and environments. Okay? A high-level abstract understanding of the algorithm's efficiency to compare algorithms across different input sizes and environments to determine worst-case behavior and scalability for large inputs. Okay? Use empirical analysis when you use empirical analysis when you want to understand how an algorithm behaves in a specific real-world scenario. We use empirical analysis for real-world behavior to account or for practical system limitations, example CPU and memory, to test how the algorithm performs with real data or specific input distributions. So for real data, we use empirical. For general and high-level abstract understanding, we use theoretical. Example, let's take an algorithm like binary search. Theoretical analysis, using theoretical analysis, we know that binary search takes O log n times because it repeatedly divides the input in half, and this can be proven mathematically. It is independent of the data on hardware and gives a clear understanding of how the algorithm behaves as input size grows. Empirical analysis, if you implement binary search on a specific dataset like a list of 10,000 stored numbers and measure the actual time taken by the algorithm on your computer, that would be empirical analysis. This measurement will depend on factors like system CPU speed, how the data is stored in memory, and possibly even data characteristics. This one, the theoretical analysis or empirical analysis for one binary search. Binary search. Okay. So factors to affect algorithm runtime, complexity, input size, computer performance. Algorithm analysis for measuring input size, space, complexity. Tn indicates the input size n for some functions t. The bigger here BACD, here sorting algorithm. The bigger the input size, the longer it takes to solve the problem. Example, the time taken to solve 5 items is shorter than solving 10 items. Measuring size by the number of bits B, here in the n's binary representation. Measuring size by the number of bits B is in the n binary representation. Algorithm analysis framework measuring runtime time complexity. How to measure? Identify the most important operation of the algorithm called basic operation. Contribute the most to the total running time. Example comparison in a storing algorithm. Compute the number of times repetition the basic operation is executed. Example of operation counts, insertion, sort. Basic computation performed by an algorithm, constant time assumed execution, identifiable in procedure code, largely independent from the programming language. Example, here example, assign value A to A equal B, comparison A, B, returning from a method. algorithm. Here insertion sort A n, array input A and of n integers, output the sorted array. This is the algorithm. We have insertion sort A, array A with n elements. For I equal 1 to n minus 1, t if t less than t equal ai. For j less than less than I minus 1 to 0, do if aj, then if t less than aj, then aj plus 1, then aj plus 1 equal to aj. Else break aj plus 1 equal to t, return a. This is the algorithm. We will do it in the lab. We write a code in the lab, or we follow this algorithm. Here, by inspecting the pseudocode, we can determine the maximum number of primitive operations executed by an algorithm as a function of the input size. Okay, for I equal this one, yeah, same here. Okay, this one, the operations, total number of operations. Okay, an example in CSS, all limits are reservedly stored. Total number of comparisons, a plus 2 plus n minus 1 plus equal n multiply n minus 1 divided by 2. This is an example. We will see how we get and solve this kind of analysis. Here operations and here total number of operations. So here n minus 1, here n power 2 plus n minus 1. Other example, problem searches for a key in a list of n items. Number of list items n, key comparison. Basic comparison is the key comparison. The problem for, so this is sometimes we try to find what is the basic operation of this algorithm. So for searching a key in a list of items, what is the basic operation is key comparison. What is the input size needed? Number of list items is n. Multiplication of two matrices. Matrix dimensions or total number of elements. This is the input size. Matrix dimensions or total number of elements. Basic operation, multiplication of two numbers. This is the basic operation. Or what is the size? Size, the dimension of the matrices. What is the basic operation? Multiplication of two numbers. Here we in the searching we have key comparison. Checking primality of a given integer n. Okay, we need to check primality. N size equal number of digits in binary representation. Here, what is the basic operation? Division. To find the primality of a given integer number. Typical graph problem, vertices and or edges. Here, visiting a vertex or traversing an edge. Okay. Theoretical analysis of time efficiency. Time efficiency is analyzed by determining the number of repetitions of the basic operation as function of input size n. Input size, running time t, execution time for basic operation. C is execution time for basic operation. C capital number of times operation is executed. Number of times basic operations is executed is Cn, capital C. number of times basic operation is executed. Basic operation, the basic operation that contributes the most towards the algorithm running time, like comparison, multiplication, division. Running time expressed as Tn for some function T on the input size n. C operation, the execution time, running time of an algorithms of a single operation. Cn, capital Cn, number of basic operation as a function of n. So yeah, number of basic operation is executed. Okay, this one, the values of some experiment of several functions important for analysis algorithm. Here, fastest growth. Here, slowest growth rate. We do this one: constant, linear, logarithmic, quadratic, cubic, exponential, other polynomials. Constant growth is independent of the input size n, Tn equals C. Example, existing array element at non-location assignment. Linear growth is directly proportional to n, Tn Cn, finding a particular array elements line search. Logarithmic growth increases slowly compared to n, Tn log n. Example, finding particular array element binary search. Binary search take log n. Quadratic, Tn n power 2, typical in these nested loops. Nested loops, we have n power 2. That's why bubble sort, the complexity of bubble sort is n power 2, because we have a nested loop. We have for I to 1 to from 1 to n 0 to n and so on, and we have a nested loop for j equal to I plus 1 to j to n. Cubic, Tn, matrix of multiplication in cube. Exponential growth is extremely rapid and possibly impractical. Tn equals c power n. Example, Tower of Hanoi and Fibonacci number. Fibonacci number is Fibonacci number. We have t power n. Other polynomials, Tn n power k. Example, typical is more in more nested loops, n power k. Tn log n. Example, sorting using divide and conquer approach. This one will consume only n log n. Okay, log n, logarithmic. N log n, sorting using divide and conquer. This is the graph for log n and t power n. Worst case efficiency. An input size of n which algorithm runs the longest among all possible inputs of the size C worst maximum over inputs of size n. How to determine, analyze the algorithm to see what kind of inputs yield to the largest value of the basic operations count. C worst among all possible inputs of size n. Compare the worst case value C worst. For any instance of size n, the running time will not exceed C worst in its running time on the worst case inputs. So here we find the worst case. If I found compare, and here we have value less than the worst case, so it is better than this algorithm. Best case efficiency as input size of n of which the algorithm runs the fastest among all possible inputs of the size C best minimum over input of size n. Like we make a comparison, like I told you, if I have the key, it is the first element, so this is the best case. If it is the last element, this is the worst case. If it is not in the list, it is the also worst case. Okay. C best minimum over inputs of size n. How to determine the kind of inputs for which the count Cn will be the smallest among all possible inputs of size n. Okay, determine the kind of inputs for which the count Cn will be the smallest among all possible inputs of size n. Compute the value of C best. Here note the best case does not mean the smallest input, but it means input size n for which the algorithm runs fastest. Average case efficiency, average time taken, number of times the basic operation will be executed to solve the all possible instances, random or of the input. Note the average of worst and best case. Neither the worst case analysis or nor its best case counterpass yields the necessary information an algorithm's behavior. See average over input of size n. How to determine must make assumption about possible input of size n. Okay. Example determining worst case, best case, and average case for algorithm. Sequential search. This one sequential search. Best case, there are worst case, there is no matching elements or the matching element happens on to be the last on the list. If it is the key in the last item, so this is the worst case, or it is not in the list. The algorithm makes the largest number of key comparisons among all possible input size. This is Cn was Cn equal n. So here n equal n under upper bound of the running time. Input is the one where the algorithm runs the slowest. Here, best case, the first element in the list equal to the search key Cn equal 1. Cn equal 1 means the first element is the key. Lower bound running time, input is the one where the algorithm runs the fastest. Average case, standard assumption probability of successful search P0 less than P less than 1. Probability of the first match occurring in the ith position of the list is the same for every I. To find the average number of key comparisons, see average n successful search. Probability of the first match occurring in the ith position of the list Pn for every I, and the number of comparisons made by logarithm in such a situation as obviously I. Unsuccessful search, number of comparisons is n. The probability of such a search being 1 minus p. Note formula on the next slide, predicting on the average running time. Here the found in the random element. Average case formula, see average 1 dot p divided by n 2 pn I pn plus n 1 minus p equal p 1 2 3 I equal n 1 n minus p equal p n n plus 2 1 plus n minus p equal p n plus 1 2 plus n 1 minus p. If p1 successful, if p0 unsuccessful. The average number of key comparisons made by a sequential search is n plus 1 divided by 2. The algorithm will expect on average about half of the list elements. If p equals 0, unsuccessful, number of key comparison will be n because the algorithm will inspect all elements on such inputs. Asymptotic notations, asymptotic definition, approaching a given value as an expression containing variable tends to infinity. Asymptotic complexity, describe the growth rate of the time space complexity with respect to input size, not directly related to the exact running time. Asymptotic growth is when n goes to infinite, thus higher order terms is more important. Three types of notations. We studied big O, big theta, and big omega. We go through this one early. Okay, here we have big O. Okay, here we have this example. Big O, big O for some example. As we see here, constant, logarithmic, linear, n log n, quadratic, cubic, exponential, factorial. Okay. So we stop here and we complete tomorrow, next week, inshallah. I will share with you the slides. Okay. So see you next week, inshallah. I got a problem in my laptop. Sorry. I'll share with you the screen. Thank you very much for attending. Please don't forget to make the attendance online. Thank you very much.